Welcome, everyone. I'm Balázs. I'm a PhD student from the Eötvös Loránd University and from the Wigner Research Center. And, I was thinking, what topic should I talk about in this conference? And usually what I see here that the topics are very specific. So I wanted to talk about something more general that is maybe useful or interesting for everyone, and only use the specific topic as a kind of plot device to talk about this topic. So the topic is cosmology and cosmological simulations. And what is cosmology? Cosmology is just the study of the origin, the evolution, and the eventual fate of the universe. And cosmological simulations are computer simulations that tries to model the formation of galaxies and galaxy clusters and whatever structure in the universe. And you basically want a simulation that is faithfully represents or reproduces the observed universe around us. And you don't need to be, I don't mean a perfect one-to-one representation or replica of the universe, but you want a representative sample that captures the physical properties or physical features of the universe you want to study with that specific simulation. And the core is actually really simple. So you can add many extra layers to these, but I just want to talk about the basics first. So this is obviously a computer simulation. You have to discretize the space. You discretize actually all the matter in the universe, either into a grid or particles. And these particles are not actual particles. These are not like actual galaxies. That's a usual misconception. But these are just effectively represent some amount of matter or volume or density in the universe, and that's all. And these particles will obviously interact in many different ways in the universe, but the most influential and most important whatever interaction will be gravity. And what you do is you let all the particles in your simulation evolve only under the influence of gravity, and by solving some appropriate equation of motion that you can see here. And this consists of actually 3 different parts here. The first part is just simply the Newtonian gravity. The second part contains basically the expansion of the universe. And the third part is what I will talk about later. It is just the boundary conditions. And what you do is you let your particles evolve from very early state of the universe, let's say 13.7 billion years ago, until the modern day now, until the present day. And then you can compare the results to, or the statistics of the results to any actual observers, or actually do whatever you want with these simulations. So, okay, that sounds simple, but where is the actual catch? And there's multiple catches, unfortunately. The first problem is that the formation of the universe is highly nonlinear. So you need, obviously, a numerical simulation because you can't solve structure formation analytically. But another problem is that usually you have so many particles that you can't even compute all the forces and all the interactions between all the particles. So you need to employ some kind of numerical trick to make this possible. The second problem, which is maybe even more critical or more brutal, is that the universe itself is really, really huge. That's obviously everyone knows that. But if you want to try to simulate a box which is the actual size of the universe, then you simply can't fill it up with enough particles to achieve any kind of usable resolution, because you can't even resolve even the largest structures in the universe with such a huge box. So you need even more tricks to make this possible. So the solution, the first problem, is obviously kind of straightforward. You just need some kind of algorithm that can simplify the force calculation in some way. You see on this first slide, or do some trick that makes it possible to trace for all particles. And that is kind of obvious. But the second problem is a bit maybe even more straightforward or have an even more straightforward or trivial resolution. If you cannot resolve the entire universe, you just simply need to simulate a smaller box. Like that, that's obvious logic. So you don't need the entire thing, but only just cut out a small box and simulate that. But to do this, you need to assert assert a couple of non-trivial things. So what is the point? I just want to reiterate it. You want a box to simulate a box that actually representative of the entire universe. And first of all, this box needs to be large enough to contain a representative sample of the universe itself. So if it is too small, it might not capture various physical processes or interactions that happens on larger scales. So you need to find a sweet spot in the size of the box. It can be too small, it can be too large. You need something in between. The other thing that since you're simulating only a part of the universe, you need appropriate boundary conditions to handle this problem. And from observations, we know that the universe is statistically self-similar beyond some size scale, so beyond a few hundred megaparsecs, and there are no coherent structures beyond that scale. So if a box contains a handful amount of these repeated units, obviously different representations, then you can say that the box is large enough to be representative of the entire universe. And everything beyond that, what you do is you just wrap around. And this is used in many different particle simulations, not just in cosmological simulations. You apply boundary conditions on every side of your box. So what goes out in one side, it comes back from the other side. That's all. And that is how cosmological simulations were made in the past around 50 years. That was the standard. So we have a solution to this entire problem. We can do cosmological simulations. No, unfortunately, that is not the it has unfortunately different problems. So when you make an actual periodic box, you're also making an arbitrary claim about the system. And in this specific case, cosmological simulations, the physical claim is about, or the claim is a physical claim about the structure or the topology of the universe. Your simulation now lives in a manifold with very specific mathematical properties. And those properties, unfortunately, we know are not the same as the properties of the universe. So first of all, I just listed maybe the three most important things about this. Take rotational symmetry. A cube has 48 rotational symmetries. So it is the octahedral group in group theory. But if you take, in this case, any kind of galaxy cluster in your simulation or in a universe that you simulated and rotate it by some arbitrary degree, then the gravitational force acting on it will change depending on the actual axis of the box, which is obviously not a physical thing. That doesn't happen in the universe to our best knowledge. But this also implies that the angular momentum in box simulations are simply not conserved, which is an even bigger physical problem. The other thing that the force law, the equation I showed you before, where the Newtonian gravity, the equation is in that equation, is unfortunately, it is also distorted in a box. So when you simulate a periodic box, you actually apply an infinite. So when you simulate a periodic box, a particle is affected by an infinite amount of its mirrored image in every direction. And obviously, you need some kind of numerical tricks. That's what I talk about to somehow trace this infinite amount of boxes or particles in the box. So you use the so-called Ewald summation, usually also used in many other particle simulations, but this will distort the Newtonian force in the original equation. So actually, all the simulations from the past 50 years weren't even Newtonian. It was just some kind of strange gravitational simulation. And the third thing that there is no observational support for this entire thing. So we know that the universe is not periodic. There were attempts to I don't know, to observe some kind of periodicity in the universe. And it was maybe in the 80s. I'm not quite sure when was this a thing. But obviously, we now know that from observations that this is not the case. The universe is not periodic at all in any way. Uh, so why we still use cubical simulations? Because in fairness, the cube is the cube for excellent reasons. For example, you can say a lot of positive things about the cube. For example, it was originally introduced because these FFT-based calculations that are very inherent and very important in obviously on almost all parts of cosmological simulations work really well on these cubical periodic topologies. You can say that translation invariance is automatically or statistical homogeneity and translation invariance are automatically works in these cubical boxes. But also one of the most important things that usually not really said about this are the practical reasons. So in the past 50 years, we built up, or the scientific community built up, an enormous scientific toolkit that directly target these periodic cubical boxes. So if you want to do anything else, you need to basically reinvent the wheel from scratch. And this is obviously not many people would do. So basically, yes, the question is not about whether a cube is useful, because it is obviously useful. It is more like whether the hidden topological assumptions that these periodic boxes have inherently, do they matter to the questions we want to answer with these simulations? Okay, so, but let me ask the reverse question to this entire thing. If we could start over, if we could create something new from the ground up, what would the ideal topology look like? And you can approach this from the following direction. You can state what kind of physical properties or mathematical properties these ideal geometry should have to even decide what you do. The first thing, I just listed 5 things, I don't know. You can obviously tell many other things. That's just maybe the most important examples. First of all, we know that the universe is isotropic. It's not a periodic box, but it has some kind of isotropic boundary condition. So your new topology should reflect it. The other thing is that angular momentum should be conserved, at least locally, because that is a very fundamental physical principle in every field. The other thing that you should obviously have a physically motivated first law, so not just some distorted gravity-like or Newtonian-like force law, but actual Newtonian geometry or something that is physically motivated. And of course, you can list many other things. But these are the most important. And there is actually a framework that achieved this, and this is the SEPS framework, which stands for Stereographically Projected Cosmological Simulations. And the trick behind this is actually very simple. So it's so simple that even the ancient Greeks know about this mathematical trick behind this. It basically, what happens here is stereographic projection. What is stereographic projection? It's basically just a map between an infinite plane, and an infinite plane is projected or mapped on the surface of the sphere. And you can do it and it's easy to describe with a very simple transformation, a coordinate transformation. And you can do it in basically arbitrary amount of dimensions. For example, in 3 dimensions, you can actually use or take the entire 3D infinite universe, and using stereographic projection, you can project it on the surface of the 3-dimensional sphere. And that surface on 3 dimension or 4 dimension will be actually a 3-dimensional sphere. And you can use that 3-dimensional sphere to make your simulations. And how does it would look like actually? It would basically like that in the middle, it's basically an observer, and if an observer looks out in any direction of the sphere, everything will lose resolution if we go further and further from the middle. And in the very middle, everything is in really high resolution. Everything in the surface or the boundary of this 3D sphere will be very low resolution, but they will basically, the entire universe will be compactified into this sphere. That's the trick. And you can take this machinery and make, for example, spherical simulations, but also you can make, for example, cylindrical simulations. And it's very interesting because there are basically two types of, or of course you can make many different classifications, whatever you like, but there's basically two classes of cosmological models. There are isotropic models and there are anisotropic models. And of course you can different classifications, but isotropic models can be well studied with these spherical construction. But anisotropic models, an entire different class of simulations that was very limited in the computational domain, can be studied, for example, with cylindrical simulations. And
sorry to disturb you, but please conclude shortly.
Oh, okay. Sorry. Oh, so, okay, I see the time. So this is how a cylindrical simulation looks like. You can literally imagine this entire thing as a cylinder. The cylinder is periodic only on one axis, and it has this stereographic projection in the other two axes. And you can see that the usual cosmological web or cosmic web also forms in these simulations. And there are very different fun things you can do with it. For example, you can actually test different anisotropic models numerically, which couldn't be done previously. One thing you can do is there is a computer scientist named Shamir who publishes the same result almost every other year, and it's very interesting because he gets a lot of citations for this. And he says that he thinks there is a strong anisotropy in the distribution of the spin of galaxies. So if you take the spin of a galaxy, it's either rotates right or it rotates left. And they says that on one side of the sky, most of the galaxies rotate to the right, and on the other side of the sky, most of the galaxies rotate to the left. And you can test this whether, okay, there's obviously many different hypotheses why that could be. But for example, we ask whether it can be due to the universe having cylindrical topology. It's just a random question out of the many. And we tested this and we get a new result that no, it is not due to the cylindrical topology. So it cannot really explain this. But okay, so what I want to say with all of this random rambling about cosmological simulations, I want to basically just summarize my takeaway about all of this, or just summarize one takeaway because I don't have time. So usually the standard periodic cube, it works really well, and it is used for 50 years, obviously, because it works really well. But this is not the only topology the universe actually allows us to simulate. And I can obviously just almost read the things that on my side. But what I'm going to say is that when they say, or when actually Newton said that when we're standing on the shoulders of giants, it should imply that we inherit not just their answers to the questions they wanted to answer, but also their questions. And I think you need to take time to learn the origin of core assumptions, for example, why the periodic cube was chosen for computer simulations, and the reason why they are there, because you might be resolve the problems or the questions in a different way, and you shouldn't be actually afraid to question these very strange assumptions or core assumptions, because you might can do better. And okay, that's it. Thank you for your time.
Thank you for the nice presentation. We have time for one short question.
So, you have these simulations on a spherical setup and in the cubic. Do you see differences in between the two? So you said that, but what are the problems with the cubic simulation? You did the stereographic simulation. Are there differences? Are there relevant differences? So what is the conclusion?
Yes, there are differences actually. So in cubical simulations, simply the force towards the corners of the cube is different than towards or along the axes. And this will distort the structure formation inside the cube. And it will affect obviously every statistical property of the entire cube, and it will cause some kind of error. Yes.